Today we are going to graph logarithms. So I just have some general graphs at the top of the page here to just go through with you. So in general, just some function notation. This is saying f of x equals the log base b, unknown. This is just not a specific graph. It's not labeled in any way, shape, or form. But what is always true is we are not allowed to have that little subscript be 1, and we are not allowed to have that little subscript, the base of the log there, be negative. So that's why that says b has to be greater than 1. This will always have these 2 points, whatever that little subscript is, comma 1, and the point 1, 0. And what I'm going to try to do is explain to you why that works with one that has actual numbers. Okay, now anytime you want to do this, you're totally welcome. But function notation, you can interchange that f of x by just putting a little y there. And I do that a lot of the time because the function notation can sometimes throw people off and think it's a variable or something like that when you see the f of x. So if that ever helps you, you can always replace f of x with y. Okay, so basically what's going on in this graph that you have here, and I'm just going to make a little tiny table. Here are the 2 points that they have marked on the graph. If the x value is 1, the y value is 0. And if the x value is 5, the y value is 1. So that's kind of corresponding to this graph over here, where it says we have the point 1, 0, which we do here. And over here it says the base, the little subscript, comma 1. And you'll see in my example here, the little subscript is 5, and 1 is the corresponding point that goes with it. Okay, so just in general, let me write this over here real quick. Like, let's say we had the log base 4 of x. So that would mean the points I would have would be the 1, 0, and then we'd have 4, 1. If we had the log base 3 of x, which we're going to do actually underneath here, I would automatically know I'm going to have the point 1, 0, and 3, 1. And let me explain why that works. So if we have our equation here, we have on the graph the log base 5 of x here. If I go ahead and actually substitute one of those numbers in, so if I substitute 1 in for x, let me show you why this is true. So y equals the log base 5 of, we'll plug in the 1. Now, why is that always going to be equal to 0? Like, how can they come up with that in their definition? What I'm going to do is have us convert this to exponential form just real quick to show you why this works. When you swing that little subscript across the equal sign, that pushes the y up into the air as an exponent. And as I do that, this is just exponential form. And that gets rid of the log. Now, what we would need to do there is figure out what we would plug in to get y. Well, the only way anything to a certain power is equal to 1, that's in your properties of exponents, that would mean if it's equal to 1, that exponent has to be 0. Anything to the 0 power is 1. So that is why that is always a point. No matter what the base is, I can say that 1, 0 will be a point. I could go through every time and I could prove that just by switching that to an exponential. Okay, now let me prove the other point to you. We would have y equals the log base 5. Now I'm plugging in what the subscript is for x. So my base is 5. I'm going to plug in 5 for x. So if I do that, same argument, I'm going to swoosh this over here, get rid of the log by switching this from log form to exponential form, I get 5 to the y equals 5. Well, anytime that would be true, since those bases are exactly the same, my exponents have to match. I put a 1 in here because any base, if it doesn't have an exponent, it's that number to the first power. So in that case, y has to be 1. And then if you look back, that's what we had in our table, 5, 1. Because what I'll have in that scenario, I'll always have the subscript, and then what I'm taking the log of, when I convert that to exponential form, that'll always be matching on each side, and then I'll have a y equal to 1. Okay, so you guys can see I totally moved the paper a little bit so you can see the bottom of the page a little bit better. So what this says here, logarithmic or log functions and exponential functions are inverses of each other. So that's what we were doing. I converted from log form to exponential form. So these are inverses of each other. This is not something that you can type into the calculator to look at the graph unless you have a base 10, and all these questions are not going to have base 10. So like the one we just did above, that had a base of 5. That's going to have a base of 3 for your log. So the process for doing this, to graph a log function, you find the inverse of the log function. To find the inverse, I don't know if we've practiced this year, so I'm going to practice this in this question. What we do to find an inverse is you switch x and y in your original function, and then you get the algebra going to solve for y or get y by itself on one side. We're going to graph the inverse, and then we're going to reflect it over the line y equals x. That's the general process for any inverse, but today we're specifically going to talk with logs and exponentials. Okay, so here's how we do this. I want to graph y equals the log base 3 of x, and they're all going to kind of take the same general shape you guys saw at the top of the page, but we're going to graph this specifically for log base 3. What I want to do is find the inverse of that. So to do that process, you switch x and y. So I'm just going to rewrite x equals the log base 3 of y. And to get the equation of your inverse, you are going to get rid of the log by solving this for y. I'm going to swing this 3 over. The subscript or the base of the log becomes the base of the exponent. So that 3, pushing that x up in the air, this would be 3 to the x equals y, which, if you guys want to look, I've already got this written for us in this lovely table, but that's the actual algebra behind it. Now, I can't put this into the calculator, the log base 3 of x, but we definitely can put 3 to the x in the calculator because that doesn't have anything to do with a log being written there. So here's what I'm going to do. What I would recommend, middle of your table, I would recommend whatever sets that exponent equal to 0 if you're working with an exponential function. You can grab your calculator here, or you can just do this by hand. It's totally up to you. Each one of these, I would plug in the x value for the exponent. So like here, this would be 3 squared, 3 to the first, 3 to the 0, 3 to the negative 1, 3 to the negative 2. You can do each one of these. All right, so this is just going to be 9. This is 3. Anything, be careful with this, it's not 0. Anything to the 0 power is 1. So when I plug in 0, I'm going to get 1. Negative 1 is 1 over 3 to the first, or 1/3. And 3 to the negative 2, remember, negative exponent does not mean negative number, it means fraction. It'd be 1 over 3 squared, which would simplify to be 1/9. Okay, now, the reason we do this, we can find those values. If you have two inverses, what happens with an inverse? The x's in the original become the y's in the inverse, which I have already done. And then what we need are the x's. The x's in the inverse are going to be the y's in the original. So they trade places. Just like I traded x and y and solve for y, if I have a table, I just trade the tables. So all the x coordinates become the y coordinates. All the y coordinates, we're just going to write them with the corresponding in the x coordinates. So this would be 1/9, 1/3, 1, 3, and 9. And if this helps you in any way, 1/9 is as a decimal 0.1 repeating, and 1/3 as a decimal is 0.3 repeating, if that kind of helps you estimate where that's going to fall on the graph. I'm actually going to graph both of these so you guys can see. So let me start with the exponential. I'm going to pause the video and do this graph, and so you guys will save some time doing that. Go ahead, pause the video, and graph both of them. Okay, so all I did was graph the first one. Actually, I want to talk about domain and range before I graph the log. So this is an exponential. We did that at the beginning of the unit. In terms of your domain, that goes to the left forever, and this goes up really fast, but it does go to the right forever. So the domain should be -infinity to infinity. That's true for any exponential function. Now, your range, remember these graphs have an asymptote, and that's going to be a line that the graph approaches but never touches, never goes over. And for this problem, it's only affected if you have something added or subtracted at the end of the equation. I just have 3 to the x, so your asymptote there is going to be just the horizontal line, y equals 0. So we're going to get really close to that and never touch it. Now, the reason I talked about that before I did the range is because that's related to the range. So this is going to curve down, get really close to this, but it never becomes 0 and it never goes negative. So the entire graph is above that asymptote, but it doesn't actually touch the asymptote. So the lowest value for your range is going to be 0, and then it points up forever. So that's going to go to infinity. Now, for your domain and range and asymptote for the log, we're going to go ahead and graph the log. So the log function here, and we're just going to estimate with these. So 1/9, I don't know, just come a little bit over the origin. That should be good. And we're going to come down to -2. And then 1/3, like maybe just kind of think about dividing that first box up into 3. Just do your best. It doesn't have to be perfect. The rest of these will be nice points. Now, 1, 0 right here, 3, 1 right here, and all the way over here, 9, 2. When you graph this, the inverses should be a reflection over that little diagonal line that I've got there, y equals x, and the x-coordinate and y-coordinate just trade places, so they're reflections of each other. Now, what's going to happen here, let me grab a different color. Your asymptote for the log function is actually going to be vertical. Okay, so I had y equals 0, and I probably should have used a different color. Hopefully you guys can see that okay. It's actually a vertical line. It's going to be x equals 0, and it'll get really close to the y-axis, but never touch it and never go over it. And then to talk about your domain and range, when you have inverses, the domain of the original will be the range of the inverse. If you have the range of the original, it should be the domain of the inverse, but let me just walk it through with you. I'm only looking at this pink graph. Okay, domain left to right. You're not touching any part of that pink graph till you just get right over that asymptote, and it's going to start at 0, but it's not actually going to touch it. It's going to get really close but never go over. And then we're going to go to the right forever, so to infinity. Now, for the range, whoops, close that parenthesis there. Now, this goes down forever. This goes very gradually, but this will go up forever. So your range here for the log function is actually -infinity to infinity, and that'll be true for any log function.